Hello everyone, welcome to my presentation. My name is Wei Feng and I'm from Alibaba Group working on Ali Cloud Infrastructure. I'm going to talk about a heterogeneous computing framework for OCP compliant accelerators named Sinian, which was developed inside Alibaba. People may be wondering why we even have this talk, or how Sinian framework has anything to do with ODSA. In my view, ODSA essentially is an enabler for chip-level homogeneous computing. And we developed a Sinian framework to maximize performance of heterogeneous computing. So it might be beneficial for ODSA to leverage a Sinian framework as well. Here is the outline of my presentation. First, why is heterogeneous computing important for data centers? Second, what are the opportunities and the challenges for ODSA-enabled heterogeneous computing? Finally, I will introduce Sinian framework and discuss its performance benefit. Let's first look at the computing demand at the data centers. As machine learning applications get widely deployed, computing power at the data center increases almost exponentially. This is because machine learning application often requires massive parallel computing with high throughput, where some other application may need a real-time response with very low latency. These applications also consume a large amount of memory with high data movements. In addition, machine learning applications are typically domain-specific, and they evolve extremely fast. So we have to somehow deal with this level's diversity and variation. Before we dive into how we are going to do optimization, the question comes to my mind: what is heterogeneous computing anyway? Here we loosely define heterogeneous computing as coordinated computation between different architectures. That is, heterogeneous computing equals one or more CPUs with one or more accelerators. It's very common for data centers to equip with various computing resources such as CPUs, GPUs, FPGA-based or ASIC accelerators. Why do we need so many heterogeneous resources? Because computing resources can provide various ability for our compute needs. We know CPU is good for general-purpose computing with fine-grained control, while GPU is suitable for parallel high throughput. FPGA accelerators can be used for coarse-grained computing, and ASIC is customized for high performance. So we have applications with various computing characters on one hand, and we have a larger pool of resources with much different abilities on the other hand. Now the question is, how do we map our application characters to the computing capabilities efficiently? This is definitely a big challenge in data centers. We'll come back to this challenge in next few slides. In the domain of heterogeneous computing, there's a noticeable trend in terms of architecture development. The first trend is architecture expansion and customization. This typically involves innovation on existing architectures, such as adding more powerful CMD units. At the same time, people are scaling out with high-speed interconnection. Third trend is domain-specific architecture for more coarse-grained acceleration. The last one is near-data computing to break memory wall. Near-data computing could be in memory, in storage, or in network. Obviously, this trend also adds challenges for applications to take advantage of architectural innovation. Now let's look at the opportunities in ODSA-enabled heterogeneous computing. What we described so far is for discrete heterogeneous computing. With ODSA, we may have new opportunities and challenges. This is because ODSA-based accelerators allow open interface and architecture to enable tight integration of various silicon dies into a single SoC. This means a single ODSA accelerator naturally behaves as a pool of heterogeneous computing resources. So data center is essentially like a large pool with many interconnected small pools. Now let's look at the challenges to map computation needs between applications and the pools of computing resources. Just as the classical compiler is used for compile various languages to run on different targets, we can solve this many-to-many mapping problem using sim compilation technology. So what is the challenge of compilation on heterogeneous resource pools? We know that performance is like a function of your algorithm complexity, memory system, and architecture. Here the architectural property is related to ISA, or instruction set, branch behavior, threading mechanism, synchronization, etc. For homogeneous system, we typically say an application is compute bound or memory bound because architecture doesn't change. However, for heterogeneous system, there's many different architectures to deal with. Thus, optimization complexity dramatically increases with much more variables, including spatial complexity and all kinds of compounding effects. To compare these two systems, for homogeneous compilation, we just need to focus on compute operator and memory operator. But for heterogeneous compilation, besides compute and memory operators, there's data transfer operators, synchronization operators, spatial parallelism, temporal parallelism, task partitioning, and so on. So we have to carefully study this challenge and exploit the soft power of optimizations to maximize the overall performance. As illustrated here, in addition to the classical optimization, such as vectorization and data reuse-based optimizations like data layout or loop tiling, there's architecture-specific or domain-specific optimizations such as kernel fusion and sparsity-based optimization. More importantly, we have to pay much attention to heterogeneity-aware optimizations, including task partitioning for spatial parallelism, multi-grain optimizations between the different architectures, load balancing among resource pools for utilization. What we just discussed is for general heterogeneous optimization. So is there anything special for ODSA architecture? Here is a simple example of optimization heuristic, which may be important for ODSA. For example, CSE, or common sub-expression elimination, is a useful technique to eliminate redundant computation. As you can see here, A times B is redundant for the second assignment. It can be eliminated by simply let y equal x. On ODSA, These two computations can happen on different chiplets due to task partitioning. Because computation chiplets are tightly integrated with high-speed interconnection, whether doing this certain optimization or not really depends on cost of data transfer and the cost of computation itself. If the data transfer is cheaper, CSE optimization makes sense. Otherwise, we can do reverse CSE or rematerialize computation to enable parallel compute among chiplets. Now we introduce the Sinian framework for heterogeneous computing. Sinian behaves like an acceleration layer between up-level application and the lower level of computing resource pools. This layer is also named Sinian Halo, meaning heterogeneity-aware lowering and optimization. Here is a bit more details regarding Sinian. In addition to common optimizations, Sinian heavily focuses on heterogeneity-aware optimization. This is also the key differentiation from other frameworks such as TensorFlow, XLA, TVM, GLOW, OpenVINO, or even TensorRT. These frameworks are either dedicated to certain architecture or only generate code for one of many computing targets instead of multiple targets simultaneously. One of the important components in Sinian is Open Deep Learning API, or ODLE. ODLE is a unified interface to abstract away underlying architecture details. It essentially decouples hardware and software for parallel development. ODLE is self-contained such that changes in underlying ODSA architecture can be completely transparent to up-level application. This is particularly important for data centers to deploy accelerators without much effort to re-optimize application. ODLE has been already supported or under planning to support by GraphCore, Intel, Cambricon, Qualcomm, and Alibaba internally. We expect more vendors to support it soon. Sinian can benefit both data center infrastructure and application development. At the data center side, it provides a unified acceleration framework for high-level applications. It is high-performant and general purpose. It also easily avoids hardware development overhead due to software iterations or algorithm changes. At the application side, it separates algorithm and optimization so that algorithm can be optimized separately. This makes it transparent, flexible, and easy to maintain. They also reduced repeated optimizations for different architectures and reduce development cost and time to market as well. As ODSA architecture evolves, what is the direction for heterogeneous optimization? First, we are continuously optimized for architecture innovation. Second, to reduce the memory war effect remains dominant. So in this regard, not only we need to optimize from software side, architecture support such as near data computing also plays an important role. Third key aspect is software-hardware co-optimization. This needs to work closely with ODSA community. This is the action list I would like to call from ODSA. Sinian will be open sourced in Q3 2020. Alibaba Group will be the maintainer of the code. We welcome contribution not only from software side, but also from architecture side, such as data transition support inside ODSA, performance counters with unified access, profiling tools, ODSA acceleration libraries with orderly interface. Lastly, experiments with Sinian on ODSA architectures. This concludes my presentation. Sinian is still an active development. We welcome good suggestions and contribution to the design and development of this framework. Please let me know if you have any questions. Thank you for listening.